Okay, so welcome to this station. What you're going to be doing is you're going to be watching this video and taking notes, and at the end, we're going to go through an example problem. This is a new page of notes, and the title is Recursive and Explicit Functions. So we've talked about sequences, arithmetic and geometric sequences, and now we're going to talk about how to write functions for those sequences. And so two types of functions we're going to use are called recursive functions and explicit functions. So your learning target today is I can explain why different equations or different functions can represent the same sequence and represent situations with those sequences. So, like I said, we're going to learn two functions here. They're going to represent the exact same sequence. So if I have a list of numbers, I can write two different functions for it, and they're not gonna look the same, but they're going to both explain that sequence. Okay, so what is a recursive function? Recursive function is a function that uses the previous term. So we've been using this a lot where you have to say, the last term was this, so the previous term plus 7 is my new term, right? So it's referencing the previous term. An explicit function, also known as the closed form definition, is a function that does not use the previous term. So it allows you to jump ahead and say, like, for the 1000th term, you can just calculate it. You don't have to know the one right before it. Okay, so here's an example of an arithmetic sequence. It starts 6, 10, 14, 18, 22. And I want to create a recursive function for this. So in order to write a recursive function, you have to have two things. The first thing you have to have is you have to say where the sequence begins. So we'll say that the sequence, our function f of 0, the very first part of our sequence is 6. So I'm calling this the 0th term, right? So this is term 0, this is term 1, term 2, term 3, term 4. Now I could have also said f of 1 equals 6 and called this the first term. All that's going to do is it's just going to change what happens when I write the function. So you have to decide, is this the 0 term or the first term? Okay. When I give you problems, it might change in each problem. So you have to be careful to notice, are they calling it the 0 term or are they calling it the first term? Now that I have that, I'm going to look for my pattern. So it looks like I'm just adding 4 every time. So what I'm going to do is I'm going to write this function. My function is equal to the previous term plus 4. Notice I said for n greater than or equal to 1. Why did I say this? Well, because my pattern starts as soon as I do the first term, right? So if this one's the 0th term, on the first term the pattern is starting. So from then on out, I'm using the plus 4 pattern. So just so we're clear, this is the beginning of the sequence. This is where our sequence starts. This is the term I'm looking for, also the function that I'm trying to write. So if I wanted to find f of, let's say, 5 in this case, I'd go 0, 1, 2, 3, 4, 5. I'm looking for this next term, right? So that's what f of n represents. F of n minus 1 represents the previous term. So if I was looking for f of 5, f of 4 is the previous term, right? It's 1 less than 5. So that would be 22 in this case. And then this plus 4 is my pattern. And then right here, this is when the function starts working. This is when my pattern begins. So this is a really, like once you get this down, you're going to be able to write recursive functions really, really quickly. The problem with recursive functions is, what if we want to know f of 100? What if that would mean you would need to know f of 0 all the way up to f of 99. You would have to know all those different answers just to find f of 100, which is a lot of work. So rather than using recursive functions, sometimes we're going to want to use explicit functions. These ones are easier to write, but they're sometimes a little less useful, okay? So the place that these are really useful is in computer programming. If you're using computer programming to write a function, then this is really, really useful. Now, an explicit or closed form definition helps us find the nth term. Well, why do they call it the nth term? Because if I'm finding f of n, the nth term is whatever term I'm looking for, right? It's a variable. It's what term I want to find. Okay, so I put this table here so we can kind of recognize a pattern. So let's see what pattern I'm kind of showing here. So right here, here's my original sequence, 6, 10, 14, 18, 22. And I'm showing how this function is kind of built. Remember, it was arithmetic. So I'm starting at the 6, and then every time I'm adding something to it. And that what I'm adding is 4. So let's remember that. So I have 6 plus 0, and I've represented it this way. I think you're going to see why in just a second. 6 plus 4 times 0. And then now I'm adding a 4 to it, so I got 6 plus 4 times 1. And now I have, well, to get to the next one, I'm going to add 4 again. So 6 plus 4 plus 4, or 6 times 4 plus 2, and so on. So every time I'm adding an extra 4 in there. Now, notice I've also decided to start this at the first term. I didn't start it at the 0th term. So I'm calling the very first part of my sequence term 1 now, and not term 0. I'm doing this because I want to show you that you can define it wherever you want. You can call the first number whatever you want, but you just have to remember what you called it and continue to use it, right? Just like we could have called north south and south north, but we just had to pick something and then we just stuck with it. So make sure that you pick something and make sure you stick with it. Okay, so here's my recursive, or not, my explicit function. So my function is equal to, well, that starting 6, notice the 6 shows up in every one of these patterns. So there's my 6 plus, well, I got my 4. Notice my 4 is right there, and it's being multiplied by a number. Now, if we want to remember what number it is, well, look at this. 0 is 1 less than 1. 1 is 1 less than 2. 2 is 1 less than 3. So the number I'm multiplying by is always 1 less than n, right? So if I do n minus 1, that gives me my number. And my pattern starts right at the beginning on this one. It works in the beginning, so I can use it. So I'm going to have n is greater than 1, greater than or equal to 1, because right here I can start using this number for my function, okay? So now we can find f of 100. This function doesn't look like our recursive function. It's way different, but it gives us the same sequence, and it allows us to plug in 100 into it. So f of 100 equals 6 plus 4 times 100 minus 1. And if I do my so I chose, you could do subtraction here, and then you get 6 plus 4 times 99. But I felt like 4 times 99 was kind of too much to do in my head. I didn't want to pull out my calculator. So instead I used the distributive property, and this is what I did. 4 times 100 is 400, and 4 times negative 1 is negative 4. And now this addition and subtraction problem is really easy. The 6 minus the 4 is positive 2, so I get 402. Okay, so this is the beauty of using an explicit or closed form definition function, is that it jumps you right to the end. You can find exactly what you're looking for. All right. Now, let's consider it with a geometric sequence. So I have a geometric sequence 3, 15, 75, 375. If I wanted to write a function here, what I could do is I could look for a pattern. Just like I did before with the multiplying by 4, I'm going to look for the same thing here. And notice that this is 3, and each of my terms starts with 3. So it's 3 times something, right? And in this case, it looks like it's 3 times 5, and then 3 times 5 times 5, and then 3 times 5 times 5 times 5. So these are all powers of 5, right? So this is 5 to the first power, 5 to the second power, 5 to the third power, and so on. This first one, we can define it as 3 times 5 to the 0 power, because 5 to the 0 power equals 1. So that's what I've done here. 3 times 5 to the 0, 3 times 5 to the first, 3 times 5 to the second, 3 times 5 to the third, and now we can see our pattern developing. So to write our geometric sequence, we can write an explicit function this way. We can define the function g of n as 3 times 5 to the n. Notice with the explicit function, I don't have to tell you where the pattern starts, right? I don't have to say g of 1 or g of 0. I can just give you the function, okay? And it's going to reproduce that same sequence. Not like the recursive where you have to define the very first term. Okay, so now that we've kind of talked about explicit and recursive functions, I really want to spell this out for us. What does a geometric recursive function look like? What does a geometric explicit function look like? What does an arithmetic recursive function look like? And what does an arithmetic explicit function look like? So let's take a look. Here's the big idea. If I want to write a recursive function for an arithmetic sequence, I need to start with a starting spot. So I chose 0 for this case, but I could have chose 1, right? And my function a of 0, I have to tell you where it starts. It starts at a number. So we're going to call that number b. Once I give this, now I can write my recursive function. Notice that a of n minus 1, the previous term, always shows up in recursive functions. Okay? So in a recursive function, I'm starting at b, and then I'm adding c every time. Now c could be positive or negative, but I'm adding it every time. So you take the previous number plus c. Previous number plus c, right? That's the function that we're going to write for arithmetic sequences, recursively. Geometric is a similar idea. You have to say where it starts. Well, g of 0 is going to start at c. And with a geometric series, we're always multiplying by the same number. So I'm choosing to multiply by b here. So b times the previous term is going to give me my next term. So the previous term times b, previous term times b, the previous term times b, and that'll give me my sequence. Now for explicit, we have these functions. Notice they don't start with a of 0 or a of 1 or g of 0 or g of 1. They don't need that. They're good on their own. Okay. Also notice that this is in the form of y equals mx plus b, where c is the slope and b is the y-intercept. So it turns out that for an arithmetic sequence, you can write a linear equation, a linear function for an explicit. So all we're doing is our function is equal to, well, our y-intercept is where we're starting from, and what we're adding every time is our slope. And then we're multiplying that by 1 less than n. Notice this is not a function. We're not saying c of n minus 1. This is not the previous term. This is a number times another number. And the number is 1 less than what we plugged into the function. Okay? Now, for an explicit geometric, we get an exponential function, which, so anytime you're writing a geometric sequence, you can write an exponential function. And this is what it looks like. You're going to take your starting place times what your growth factor is to the nth power. So if our growth factor, if we're multiplying by 3 every time, that'd be 3 to the n, or whatever number we're multiplying by every single time. Okay, so that's an explicit geometric, is an exponential function.